All right, and we're back. So again, this is the rest of section 9.1, finally. So we were talking about rho. If rho is, if you say your null hypothesis is that rho is 0, you're saying that there is no correlation, right? A 0 for your R value is no correlation. So if you can reject that null, you can say that there is some type of correlation. Now, remember that when you state it like that, you're just saying that there is a significant correlation of some sort, positive or negative. If you say that your null hypothesis is less than or equal to 0, that means your alternative is greater than 0. That means that there's a significant positive correlation, right? Significant positive correlation. So if you can reject the null hypothesis, you can say that the alternative is therefore accepted and say that there's a significant positive correlation. And then same thing here for if we put the null hypothesis as a greater than or equal to 0, that makes our alternative less than 0, significant negative correlation, right? All right. Now, a couple things about our test statistic again. Our test statistic is T, right? We're going to be using our T tables. The test statistic T is R divided by the square root of 1 minus R squared over N minus 2. So what are the only things that we need to know to compute this formula? You need your R value, which is your sample correlation coefficient, and you need your N, which is the amount of things that you have, right? The amount of sets of data that you have. Remember that your degrees of freedom is N minus 2 degrees of freedom. N minus 2, because you've got 2 samples. N minus 2 degrees of freedom. So we were in the middle of this problem when the announcement came through, right?
Yeah.
We paused the video. Never was able to start it. So here we are. Using the following data, can we support a claim of a positive linear correlation? So what we have here is our null hypothesis is that rho is less than or equal to 0. Our alternative hypothesis, therefore, is rho is greater than 0. And that's our claim, right? Our claim is that there's a positive linear correlation. Our claim is that there is a positive linear correlation. And if there is a positive linear correlation, then our alternative hypothesis has to be rho greater than 0. That means our null hypothesis is less than or equal to 0. So if I can reject the null hypothesis, I can therefore state that we can support the claim. Right. So let's see. We've already done the process of putting it into our lists: 1, 3, 4, 5, 9, 10, 9, 15, 17, 22, 30, 35. And then we can go out here. Stat calc 4 is our linear regression. And that's where we get the R value of 0.9938. So that's where we're at right now. Right. Let's figure out our test statistic. Right. Let's figure out T. Okay, jumping back to our formula here, T is R divided by the square root of 1 minus R squared over N minus 2. R divided by the square root of 1 minus R squared divided by N minus 2. That bottom is really kind of like your standard deviation of your R. All right, so let's figure out what this is going to be. So that's 0.9938 divided by the square root of 1 minus 0.9938 squared over N minus 2. Well, N minus 2, that's our degrees of freedom, right? So 6 minus 4, 6 minus 2 is 4. So let's go into our calculator and plug those numbers in. We got 0.9938 divided by, start a parenthesis, we've got to do a square root of the whole chunk, 1 minus 0.9938 squared. Oh, got to end my parenthesis, then square it. No, I don't. Got to square it, then end my parenthesis. And then divide by 4. Right. Whoa, huge T value. That makes me think I did something wrong. I'm going to recalculate that just to make sure, because there's a lot of parentheses going on right there, right? So let's do this. Let's go 1 minus 0.9938 squared. Let's hit enter on that. Divide that by 4. Square root that. And then we have to take 0.9938 divided by that. my answer. Okay, I was not wrong. 17.88. 17.88. Okay, pretty much anything I'm going to be able to reject a null, right? I could go with the alpha of point like 0.0001 probably. But I'm not. I'm going with an alpha of 0.05. So let's pull up the t-table. You know what? Do I have one up here? No, that's not the right table. Let's pull up our t-table. Statistics here. I believe it was chapter 6. Yeah, t-distribution. All right, our t-table. We got degrees of freedom 4, and this is a one-tailed test. Degrees of freedom 4 with a one-tailed test of 0.05. Degrees of freedom 4 with a one tail of 0.05. Our rejection region is going to be 2.132. 2.132. 2.132. So our rejection region was if we could fall above 2.132. Were we successful? Quite successful there. So we can definitively say that, well, 17.88 is greater than 2.132. So therefore, we can reject the null, therefore saying we can support the claim. I'll just end it there. We can support the claim. And what was our claim? That there is a positive linear relationship. At the 0.05 significance level, we can say that we can definitely support the claim that there is a positive linear correlation between these things. Okay. All right. Now, there's an important distinction, and the book, this is the last part of this section, section 9.1. There is a very important distinguish the difference between the words correlation and the words causation. I actually teach this to my Algebra 1 students. This is actually part of our Algebra 1 curriculum now, and it shows up on our state test from time to time. The words cause and correlate. Cause and correlate. Those are very, 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 very big difference. If there is a strong correlation between the two variables, does this imply that there is a causation relationship? No. No. It does not say, even if there is a super strong correlation, even if there is a 0.99999 correlation, it does not necessarily mean there is a causation relationship. Okay? Correlation does not mean causation. Correlation does not mean causation. Correlation does not mean one thing is causing something else to happen. There could be extraneous factors happening. Okay? There are 4 possibilities that one must consider. Is there a cause and effect relationship? Is there a reverse cause and effect relationship? Is there a relationship caused by a third variable, or is the relationship a coincidence? Right? Because for you to be able to say something is a causation relationship, look at the cause and effect. Look at the cause and effect. Does one thing force something else to happen? Right? Does one thing force something else to happen? Like, I think about it like this. If I think about the days in December, the days in November and December, and the average daily temperature, right? As time passes on, that forces the temperature to go down, right? I mean, I would consider that a cause and effect relationship. I am increasing as time goes on, and therefore the temperature is naturally going to go down, right? It must happen that way, unless we defy the laws of weather, I guess. Then it's generally going to trend downward, right? Is there a reverse cause and effect relationship? Is the relationship caused by a third variable? Now we have to investigate that because, okay, I like to think about it this way. The number of hours of sleep you get and your grades, right? I would generally say the more hours of sleep that you get, generally the grades of that student is probably going to go up, right? I don't know. Is that true? Because if those students are staying up a little bit later, are they doing homework? Probably. Okay, I could go with my original hypothesis. Now, some of you might say, "Well, actually, I've been studying it." Yeah. Um, so is it is something is there an extraneous factor rather than a cause and effect, right? Like what I'm saying there is, okay, does sleeping more force your grades to go up? No, right? It may lead to something like that, right? It may lead to, oh, that means that I'm going to be more awake in class, and if I'm more awake in class, I'm paying attention more, and if I'm paying attention more, then my grades are going to go up, right? So that may be that third variable going on there. And then is the relationship a coincidence, right? Obviously, you could find trends in data in pretty much anything that you really wanted. You could find a set of data that might prove, I don't know, the shoe size, the size of your foot, and your statistics grade somehow correlates. I don't know. You might be able to show that somehow. I would say that relationship is a coincidence. So there's some things that you have to consider. Think about cause and effect relationship. In general, if we say that two things are going to relate to one another, correlate to one another, that does not mean that they are going to cause one another to happen. You have to look a little bit deeper to see if there's a cause and effect relationship. All right, I am done with the notes now for section 9.1. Finally, and we